deadline 是 Larry 有个 deadline 是吧？这个星期 Larry 可以交吗？这个星期还有几题啊？还剩几题？还没有做，还没有 try。OK，这样这个礼拜可以做吗？啊，因为I mean like at the end of 这个 semester right，you guys will submit 这个 revision homework。So throughout 这整个 semester，你都要一直在改，一直在改，一直在改，OK 吗？As long as 有新的 input 进来，你都要一直改。那你 feel 一下我讲做 lecture 咯，然后跟我一起做 lecture 咯。OK，so 你就一直改吧。所以你一定要，so the most important thing is 你要一直要有进步，一直有 like progress，yeah，OK 吗？就不管你做的好不好，先交一份，然后我们再改，一直修，一直修，修到你这个整个 sem 把它修到最完美，然后你就学到最懂，OK 吗？Make sense？OK，还有Larry 的 exercise，还有晋升的，也是这个礼拜打完是吗？OK，就 at least 打完先。失踪失踪人口啊，我来打。哦，OK，我没有看。呃，想一下，OK，so 那失踪人口哈，I think I need to contact them 嘛。So I think last week 的是汉伟哈，this week 是 Ivan 咯。嗯，如果没有的话，maybe 这2个 week 会暂时没有人打啊，maybe 啊，我还不知道，depends 啊。一的看呢、我们要把后面那个移上来做还是怎么样？我觉得给他们机会一下，不然什么？嗯，为什么杰西卡很多？哇，OK，因为怎么说呢？你换后面的给他，他后面也打不出来怎么办呢？可能后面更重要哎。哇，这样是很多。No 了，I think 我们也要给他们一点机会，给他们犯错的机会啊，让他们被惩罚的机会啊。我们不可以连惩罚机会都不给人家嘛，对不对？这样就是哈，怎么很丑？哎，这样，OK，说给人家犯错的机会吧。我们有我们自己的工作要做也是。OK，so later I think we put the quiz to the last later in the end. But if you want, you can have a look on your last quiz. Recommend you have a look because I changed the distribution a bit. So it's a 6+4. So you see what score you get. If you think not reasonable, you can discuss with me. Hey, calculus? Not calculus. Huh? Oh, Eric said turns out that the question come out in his GRE test. GRE mathematics. Yeah. So we do revision for him. Okay, this is the quiz later. Okay, later that you see. 嗯，我都跟你讲啊，Topology 的题目越长的东西越短。Okay, so okay. So later I'll let you see again the question. Hopefully not too challenging. Hey, today is lecture how many? No, part 9. Oh, 9, 9. Oh, because this is the second lecture. Okay, because we short of one lecture, right? Oh, okay. So before we continue with covering space, let's discuss the one that we left last time. Last time we were discussing We're discussing a cell complex built up by the fundamental group equal to Zn. Okay, here. Okay. So what I didn't tell you was it's not just the twist, but you need to attack the twist along the boundary. And then that will be the cell complex that have a fundamental group of Z. So for example, this Z3 here. Okay, so you should think of this Z3 as a boundary of E group. Okay, so you can see that if the boundary of E group is S1, right? So you can see that what happened to this S1. Okay, it's like curling around twice, 3 times, okay, before coming back to the same other subgroup. And see how you pick one starting point, and then you go around this S1 here. Okay? So it seems like if you like, you should see something like this. See something like this. So you circle, right, and then so maybe start here, circle, and then you circle, and then how to circle, circle like this. Okay, how to go down, and then go up. Okay, make sense? Okay, so this is the Y thing. So for general one, you go down n times, and then you need to state this around this boundary. Yeah. So yeah. Okay. Right. Okay, this is the one that we left last time. Okay, so let's continue. So next, we'll talk about covering space. But the covering space here, actually, you see this idea before. Is actually when we were finding the fundamental group of S1, right? Okay, fundamental group of X1. We said that any continuous map into S1, we can actually have a lift. Okay, with this special P here. Okay, so today we will make this P generalize, this F tilde also generalized. Okay, we'll generalize these things. Okay. Yeah, so although I draw it like this curly line here, but really this is a real number line here. Okay, so we just curl it with let's say 0, 2 pi minus 2 pi like that. Okay, so we'll generalize this idea. So to do this, we'll define what's called a covering space. Okay, so P is a covering map. So R actually is a covering space of S1. So let's define what's covering space here. So although you see a lot of word here, so let's pick up some very important terms from this definition. So a covering space of a topological space X is another topological space, okay, with a map, okay, from X tilde to X. So there's one very important property you need to remember this when you want to check covering space here. That is, for every point in X, okay, there's an open neighborhood such that if you look at the inverse of this open neighborhood, you can write it as a disjoint open set in X tilde. Okay, such that each of them will map homeomorphically onto U by P. Okay, such U is called evenly covered. Okay, if you have this kind of open neighborhood, it will be evenly covered. And the disjoint open set in S tilde that project homeomorphically to U by P are called the sheets. Okay, so how many sheets? So if you let's say if you pick a point in x1, right? Okay, you look around a neighborhood like that. Okay, you can see that there's a bunch of pre-image here. Okay, but if your neighborhood is too big, then your pre-image might not be disjoint. For example, if you look at the whole x1, then your pre-image is everything. There's no disjoint open neighborhood. Okay, but if you pick small enough open neighborhood, then you will see that the different sheets and different sheets, different layer of pre-image. Disjoint of open set 代表一个 Okay, let me see. So do we need another thing is mapping has to be homeomorphic. They need to be homeomorphic. So meaning injective, surjective, continuous. Okay, otherwise if you take too much, it won't be injective. Or it have to be homeomorphic. So the idea of homeomorphic is like whatever happened in the codomain open set, I should be able to see what happens in the pre-image. You mean if it is homeomorphic, why do I need onto again? Let me see. Two, you mean onto is not necessary. Let me think. If I put subjective, also not doesn't matter, correct? English also obviously not doesn't matter, but 重叠. Let me think. Is it necessary to put onto here? Or this is a English onto? Well, obviously I take from Hesher, so yeah. What do you mean I'm not logic? Even if it's subjective, it doesn't matter also. Yeah, could be English, I think. But if it is subjective kind of onto, then or it should be English onto, right? Because the subjective onto is a adjective, is not an adverb, right? So it should be the English onto. Yeah, yeah. Okay. Mystery solved. And let's go to the next one. Okay. So if U is connected, then you should expect that these sheets here are also connected. Okay. So in this case here, they are actually uniquely determined by U. But when U is not connected, the decomposition into sheets might not be unique. And then other thing was, okay, the third thing is pretty important when we want to count these sheets here. The number of sheets over U is the cardinality P inverse X for X in U. Okay, so for example, the real number covering X1 here, the sheets here will be infinite. Okay, they will be infinite. Could you come up with a finite covering here? Finite sheets of covering? Huh? Yeah, exactly like what we did just now, this one. You can think of this as a covering of X1 as well. Okay, obviously you need to prove that, but I think it's not hard to see, to argue loosely like that. Does it make sense? Yeah, so this is like sheets three, the cardinality of the sheets is 3. Okay, let's look at some example. I think this example is one of the example in calculus 2, I guess. So here is a helicoid surface. So parameterized by 3 cos 2 pi theta sine x sine 2 pi theta and t. So how do you expect this helicoid looks like? I already plotted with GeoGebra here. Okay, so one I look from the top, and then the other one I look from the side. And so you can see that you got these, okay, these like how say rotating, circulating around this z-axis here. And so R is infinite. Okay, so meaning your circle is building infinitely. But your S is also infinite actually. Okay, both sides actually is infinite. Just that this one I restrict my S. For this to produce this picture, I restrict my S. Otherwise, you will see a plane. Does it make sense? I restrict this S to I think maybe some like that. So if you fix the X, it's like you fix the maximum radius you can get. Okay. And you fill it out. How to say? Can understand or not? Can understand? Okay, instead of drawing this on the plane, right? But your plane is like constantly moving up. Okay, so like you swipe one like this. It's like a ladder or staircase. Okay, rotating staircase. Okay. So now what we want to cover, we want to cover this R2, punched R2. Okay, we remove the origin. So how do we do it? We just simply set X, Y, Z to X. So also you can notice that we didn't cover the z-axis, right? Because S cannot be here. We are not covering the z-axis. Okay, so we are covering the define the covering map for punched R2. Oh, speaking of this, yeah, you can check that this is covering. There's one thing I want to share with you. Do you guys know the get house? Get house near the where is it? Southgate or Northgate? B1, near B1. Yeah, do you know the get near B1? So there is a SMUM here, right? If you look from outside, so there's a security here, right? Correct or not? So if you are driving or you are following people's car to come in, do you feel dangerous when you drive in here? Why? Too short. Go inside too short. You cannot see, yes. Right. So the thing is you cannot really see a car from the right here. Okay. 什么？看了没？看哪里啊？对面有放吗？几时放的？I didn't notice. Okay, maybe there's a mirror here. 这边有 mirror？有没？有。Okay, I didn't notice. Okay, never mind. But before the mirror thing, right, I also feel like very insecure, right? You know what happened? You know why it happens? Initially, there's no this kind of problem. Okay, for those who like first time, come to SMUN in the very early stage. What happened was there are really only two roads. So going up to the D block side and then coming out from D block. There's no A yet under construction that time. So that time is quite secure because you can just leave. But now the problem here is once you create this block A, they open out the road from right to the left. So there's a self-intersection here. This is the main problem, the self-intersection. This is the singular. So accident could happen in the singular. Okay. Yeah. So one way to do this, maybe you can build a flyover. You build a file over here, then solve the problem. I think it's costing too much here. But then, yeah. Okay. So I think mirror is a better solution. Huh? Sorry? Blow up. Yeah. Yeah. Right. Okay. Yeah. Do a blow up here. Yeah. So this is one of the thing I want to share. Okay. Continue. Any homeomorphism actually is a covering map because you need a homeomorphism. If you have two covering maps, you just say the product is still a covering map. Next will be very interesting. This is the one of the basic example that maybe you want to look very closely. So let's look at the x1 cross x1. Sorry, x1 wedge s1. Okay. So last time we learned that the high one of this space is Z, free product with Z. So now we're going to define its covering space. I'll call it a two-oriented graph. Okay, two-oriented graph. Two-oriented graph. So to make sure that this covering space have a local homeomorphic property, can you look at this space? What kind of local property that you want to preserve here? You try imagine you are an ant walking around this space here. So if you walk to one place, what's the nearby scenery that you can see? Then again, you have a crossroad here, right? You have a crossroad here. So again, you have a crossroad. If you are an ant, you're walking on here, you must see four edges coming out. Okay, this is one of the locality you want to preserve. Okay, but if you walk far away from this crossroad here, really you just see like something like a real number. Okay, and then when you come back to this crossroad again, you see this locality here. Okay, so really there are like two types of things you need to preserve in your covering space under homeomorphism. Okay, so later you will see a table of them. Okay, so these are the possible covering space that you can make. Maybe by 1 year. For now, you cannot appreciate what the a square b square thingy, but I mean throughout the discussion or later we will introduce it more formally than you know what is going on. Basically, these are bracket of some generator here. Okay, so let's discuss for the picture one. Why is it the covering space? You have a point with four edges coming up, and then so what's the covering map here in this case? So how do you define your covering map? So the two intersection point here should be get sense to this wedge point here. Okay, so if you look around the pre-image of this two pre-image point of wedge point, you see the AABB beside it, the AABB edge. Okay, on one side you should have A coming up and then A coming in. On the other side you should have B coming in and then B going up. Okay, is it true in the pre-image case? You have B coming in, coming out, and then A coming up for both pre-image. Flip doesn't matter, but I think as long as 你 flip 你转个头你就 flip 了嘛，但是还是长那样嘛，对不对？是不是这样讲 ？Okay, the locality preserve is fine. Well, I mean, doesn't matter. Taiwan. Okay, later we'll see what's going on here. So if you look at here, if you look at the bottom here, if we fix this base point here, looping one round is a loop, looping A one round is a loop, looping B one round is another loop. But if you look at the covering space, right, what happened? If you choose a base point, okay, two of these wedge point here, you choose one. So you make the both ones on the left. So let's keep that one as a base point. So if you choose that as a base point, what's your loop then? Then your loop will be A, okay, A coming back. But B is not loop anymore. B you move to another pre-image, but you are not choosing that as the base point. So to be a loop, you need to go back to the same base point. So you need to do B twice. Okay. And then there's another loop, which is stated that you walk B, you walk A, and then you walk B inverse. So the claim is this tree will generate all the loops inside your covering space. But remember, at this base space, the loop is generated by what? A and B. It's a free product of A and B. So actually, in the bottom, there's more loops than your covering space. Does that make sense? There's more loop in your space than your covering space. I mean, I don't want to use cardinality, but the idea is a subset. Okay? The idea is a subgroup. Subgroup. There's a group factor. Subgroup. Yeah. Isn't it? A also inside the is also inside the fundamental group of the x1 plus x1, right? B square also, right? You take this out, and then this as well. Okay, so actually it's a subgroup of the pi one of x1 plus x1. So this is maybe one thing you want to note here. Or maybe I just go like this. Can I do this? I don't think this is. Just write this up. Yeah. Sorry. Oh, instead of use B to go back, you can use B equals to go back. I think they are two. They two. You can generate. You can because B square is identity here, right? Using the free group language, B square is identity, then B equal to B equals 1. Does it make sense? So either you use B to go back, or you can go back with the other B, but it's still a loop. Okay, use the group language. B is equal to B equals 1. Okay, so you just need to check one property. That is to make sure your that every point there's an open neighborhood that's evenly covered. Okay, and then such that each part of the is homomorphic to the open neighborhood. Okay, so first non-trivial one is to check this wedge point here. So what's the pre-image of this wedge point? Okay, so you should define that your P will send this to wedge point in the covering space to this wedge point, and then check that it's homomorphic. So meaning nearby this point here, there's a disjoint union of open set that map homomorphically. Okay. Okay. And then for all the rest of the point, I think should be obvious. Correct. So let's say for example, let's pick maybe around B here. Okay. So where's the open neighborhood of this? Middle, right? Okay, but I pick slightly to the end of slightly towards the end from the middle. Okay, so should be somewhere here, the open set of the green open neighborhood. Does it make sense? Because this is the orientation of B, right? Okay, if I pick slightly left, under this map here should be also slightly left. Okay. And then if you look at some open neighborhood around A, that's not near the wedge point, you should expect something like this. Okay. Mapping homeomorphically. Does it make sense? Make sense? Okay. So how about number two? Okay, can you see what's the P map here? If I draw this, what's the P map? So the two wedge point here also send to the stand wedge point in S1, wedge S1. Okay. So do you see that there are P, B going in, coming out, A going in, coming out at the two base, the pre-mesh of the wedge point? And so here, come in, come out, A come in, come out. Okay. So on the other one is the same, A coming, come out, and then B coming. Okay, but something to note here is if you fix a base point, the group of loops here change. Okay? A is no longer a loop here, but A square is. Okay? A square, B square, and AB. And the claim is this tree will generate all the loops inside the space. A is no longer a loop because A moved to another pre-image. But we are not coming back to the same base point yet. So okay. So how many sheets? So this cardinality is what? The number of sheets here for number one is 2. The sheet of 2 is also 2. And then maybe we can look for 3 here. So this here is the number of sheets 3. And the wedge point got 3 pre-image. And then these 3 pre-image here also have A, B coming up. Okay, and then you can see that the loops also changes.
Maps the ways were always just an example that R is not that.
So what do you mean?
I mean, if we treat R as a covering place of S, then it's no longer complete.
Depends, right? You can go up and then come back like that. But this is a contractible loop, huh? Yes. What do you mean? So the contractible loops inside pi 1 will be just constant loops. Huh? Meaning, okay, one thing close is you almost want to you almost see that actually if I have R1 as a covering of S1, then pi 1 of R actually is identity. So there's this is a trivial loops. Huh? Yeah, it's a subgroup, right? Just now we observed that it's a subgroup, so it's fine. It's a subgroup. So actually, that covering actually is the largest, but with the smallest fundamental group. Later we'll see why is it the largest covering that you can put on the S1. Okay. Yeah. So this is if you learn Galois theory before, right? This is the correspondent. So on the subgroup side, it is getting smaller, but on the space side, it's getting larger. I will make precise what larger means. It's a contravariant function. I mean, no, this is not a functor thing. This is wait, let me think. No. The contravariant functor is about a function. This is just a Galois type of correspondent. Galois correspondent meaning on one side, okay, on two sides there's a inclusion. But huh? You can
just treat the inclusion as a function.
How could inclusion be a function?
Yeah.
Anyway.
Okay. Sure. I think I get what you mean. Yeah, I think I get what you mean. Okay, never mind. Okay, so then from this idea here, you can draw more covering space here. Maybe from here, maybe you can pick one that we haven't discussed, you think that is very interesting, and then we can see why they are covering there. Or you guys are happy about there being the covering space now?
Covering space S1.
Which S1? Yeah, which one you want to discuss more? Maybe you can discuss two more. Huh? 15. Wow, you picked the monster. Okay. So how to understand this? Obviously, you see all the points with all these have to be the pre-image of the wedge points. But where's the AB? Maybe you can think of A going this side, B going upward. And then you will get. So how to grow this? Any one of you did dynamical system in this class? No? No one did. Dynamical system. Okay, so actually, you grow this complex as a fractal. Okay, so meaning when you zoom it in, right, it still looks like that. You zoom it in, still looks like this. Zoom it in, still looks like that. Okay, so how to do this? So across this edge point here, you will grow a B upwards. Okay, and then let A extend. And then when B extend up, you will grow another A upward like that. So once you got an A, put a B, put a B, put an A, put an A, put a B like that. Can you understand or not? Oh, basically, project about it. Good. Okay, so this is like a fractal. Okay, people call it a fractal. So you can extend infinitely many times. Okay, so the basic shape is just a cross, and then you put cross at every edges. Every edges are every possible edges. 没有画完，没有画完，画不完。怎么可能画得完？因为你再画的话，这边会撞到这边。如果你没有把它变小的话，它会撞上去的。所以你要把它变小变小。Okay, so this is the fractal. So why is it a covering space? So you need to check that there's a homeomorphic disjoint open pre-image. Get that meant to S1 versus S1. Yeah, 很多 infinitely. 这个是 infinite sheets. Then this is the infinite sheet. Okay. So you can think of this sheets as a layer, as a level. Okay, which level you are in. So in this case here, there's an infinite level. You can stare at the different part of your term. Previously, we only have 2 levels. Okay, so you go to second level, you come back, you become a loop already. But this one to be a loop, you depends on where you have to go and then you come back. Yes, you can come back. Actually, this is a similar type of covering space as R to S1. Okay, so to come back, you cannot loop around. It's just like you need to go stun. Okay, go backward. Yes, every loop inside this space is actually true. Okay, so this pi 1 of this space is also identity. Yeah. Listen. Yeah, can. 我不会跟你讲 identity 呢，就是这样啊。对呀，就 constant loop 嘛。Yes, this is the largest covering space. Okay, maybe I can tell you a bit more already. So the largest covering space meaning this covering space to cover other covering space. Huh? Yes, this can cover all the covering space. This is the king of covering space. Yes. Okay. Others okay or not? 还是要讨论嘛？这个圆圆的应该 OK 吧？后面这几个 maybe. So 12 嘛 13, 14 a bit like a bit getting more like a fractal like thing. Maybe 11呢，有点像个鸟坐在上面。This group is very interesting, like this B to the N A, B to the N inverse, N B to the B to the S.
哦，很轮啊。
Yeah,
那个他们baseline change 模一样。
Yeah, kind of. Yes. Because if you hit once here, right, if you move forward and then you move backward,
所以如果它有地方没有闭合的话，那就得这样打分。
没有吧？你可以停把那个 fractal，但是
没有，我的意思就是，如果你还有回到那个点的话，如果是让你尽量一直延伸到镜头。
Yeah，因为你让那个镜头无止境。Anyone know what Eric is asking? He asking why we got this fractal situation here. Why not it like stop there? Can we just stop the fractal somewhere? You cannot because if you are an end, you should come back to the same point. So either you close up or either you make your endpoint infinite. You thought you already come back, but actually not. Does it make sense? Huh? Yeah. Yeah. Oh, wow, this is a hard question. Huh? So from here, he observed that because these are you can get subgroup of your covering space.
Oh, so he is trying to ask
for every subgroup of a group, because we proved that every group is a fundamental group. So, and every subgroup of a group be a fundamental group of a covering space. This is a hard question. Well, we left it for you to figure out. I think for now, I think will we cover this? I think maybe it's a hard exercise. Maybe it's a hack exercise. Yeah, let's think about it first. I forgot whether I covered it or not, but no, it's not true actually. It's not true. It's not true because you have this covering space quite restrictive property. You need the homeomorphism to exist, so you cannot simply pick your subgroup to make it a loop, because sometimes the element is not a loop. I mean, there's no way to make it a loop. Even if there's a way to make it a loop, you need to make it homeomorphically. There's quite a lot of restriction. I don't think it's true. It's not true for every subgroup thing. You need to, yeah. You need to at least make sure that downstairs you are the loop first. Only then you can use that loop to build your subgroup of loop. Okay, I don't think it's true. It's not true for general. Okay, right. Let's see. Should we break here? Yeah. More question or got last question? 7 and 8 like a samurai. Not samurai. What do you call that? Okay. Any more thing you want to ask about these? Or if you ask me how to prove the generation of the space, the loop space, then I think we will do it later. Hopefully. 5, 6. Wow, okay. Very neat. Oh, guiding stick. Guiding stick.
就这样卷啊，给它
Potato stick. Okay, so you can see your fundamental group actually get easier when the space gets more complex. Then your generator get lesser and lesser and lesser. In particular, look at 12. 12 is very interesting. The only non-trivial loop is generated by A. B is trivial. Because if you move along B, you have to move the same way back. Then it will be complete. Yeah. The only way to come back, once you fix a base point, you have to use the same group to come back. Amazing. Because you remember the locality and the wedge point. Yeah. You have to have any coming in from the identity.
所以像左边那个那个是 inverse。
Yeah, if you want to work that way, it would be inverse. Yeah. Hmm. 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 So, okay, okay. Yeah.
哦，
大大的那个 adapter，现在是香港子。哦，Lydia got one advice for us. Please don't use U green adapter. Adapter lah. Yeah, don't use the adapter kind of U green. U green. He say will damage your iPad. Possibly. It's related because if you don't have iPad to use later, you cannot do revision. Okay, let's take a break until 3 o'clock.
可是那个牌子不是有 warranty 的吗？
希望那时候走的时候，他就拿多一个 iPad 出来给我看，
也是那个问题，
爆炸。
他也是用 U green，这样可能是那个 U green 牌子，
是有一牌子，
iPad
可能是
那个 model 的问题。
Apple 很有用诶。
你看 is the fact that 那个 adapter 很多插的时候，如果不是正版的就
可是我现在用的是，我虽然是用翻版的，但是我用的线是会控制我用的线是可以控制那个电量的。它如果小的时候，它就会很快，但是它已经差不多80%，它就开始变慢了。我不知道是 U Green 还是什么之类的，也是那种 Shopee 买的，可以 try 它，它是控制的，因为我要 fast charge 嘛，然后它那个可以 support fast charge，然后
对，OK，你这 relation，如果你拿个那叫什么呀？你一定要用 free product，还是用 free good 就够啊？
你看这个，你看这个，
这 relation，
这个
你是哪？因为之前我们是学一个 group 和一个 presentation，
对，
然后 free good portion 这样还有 relation，
嗯，
然后在这里是讲什么意思？
哪一个？这个，这个，
是有
这个是 picking out 那个 subgroup of loops，会 form loops 的一些 subgroup，就是在这个 covering space 会 form loop 的一个 subgroup，
那怎么
或者说 pi one 是它 generate。pi one of covering space，
它要讲 relate to group relation？
什么意思哦？Group concatenation 就是一个 group operation，不是 path concatenation，loop concatenation 是一个，
台湾的，
嗯
台湾的
嗯，I mean 这边有乘法，有 inverse，有 identity，哎，什么意思？因为你这个 pi one 里面的 element 也是 like，你 pi one of x1 wedge x1 是 generated by AB 嘛，那你里面的东西就是有 A 在里面哦。And then 你会有，也是会有 B square 嘛，也是会有这些嘛，但是你还有其他嘛，对不对？把这些东西是这些不属于你的，这些不属于你的 covering space 的 loop，对吗？所以它 pick up 一个 subgroup
限制还
啊，对，有些本来是 loop，结果去到 covering space 说不是 loop，
你这个模式，你这个模式的话，这什么都可以搞，不管你的 original space 长模样了哈。
不是，我的意思是说可以 cover 所有的 covering space，其他的 covering space，
I mean，like 现在我们选的是 SE West SE 嘛，
对，它所有的 covering space 可以被它 cover，
就如果我让这个比放什么 space 都好啦，
它有自己的咯。 它有自己属于自己的一个 monster，这个
啊，
最大的那个，
一样 relation 只是 monster 长不一样。
它的排王一定是 identity，长不一样，obviously 啊。
我问人家短时间怎么样扩散的体验，这个包括这个包括一个 idea 啊，对的，所以包含这个 idea 的球感。那个这个是。
哎，你们今晚是什么 event 呢？你们他们是 online 还是 physical
online
online 啊？啊，我觉得奇怪啊。
懂吗？那确实很
包，
那确实很奇怪。
挺包，好像会有点尴尬的。
那
要看啊，
谁去请啊？谁去请？
没听，我啥都不知道。
郝少奇，
我们学生会不会开会来讨论一下这个？
对所有 group 其实那个是一个版本的。
是啊，我们 prove 了，是 every group is a fundamental。
by taking 它所有的变成 identity 的一个 word concatenation 也是
对啊，
对，然后你要粘一个 to cell 上去。不是，喂，你在讲没有，你现在在讨论什么？
哎，我突然在想，
你现在是讲 group 讲变 fundamental group 对不对？你有generator 跟 relation 嘛？你的 generator 就是一堆的 loop，然后对 generator relation 还是 to cell？
哦
generator 是 loop，然后 wedge 在一个 point 上面，然后你把 to cell 沿着你的 relation 装上去，因为它那个 relation 等于 identity 嘛，意思说这个 loop 是 contractible，所以你的 to cell 会帮你 contract 这个 loop。
哎，所以我这边的这些图其实还没有粘东西上去。
这个东西没有粘东西啊，所以才是 loop 啊，不然不是 loop 的话，我怎么写把它写出来？ these are not, these are real loops. There is not no two cell inside here. If I stick any two cell in between any two loops here, then it will become a trivial loop. Okay, so yesterday actually we make a very strong conclusion. Every fundamental group is a group. This one is very normal, but every group is a fundamental group. This one is very strong. So how to do it? You write your group using group presentation, and then every generator become the loops S1 again, and then wedge together at the point, and then you glue your two cell based on your relation, because your relation tells you what is the identity map. Identity loops. So to produce this identity loops, you need to make it contractible. So two cell can help you to contract the loops. Okay, contract the relation. Yeah, contract the relation. Yeah. Okay. Next, we will discuss lift as well. So, yeah. 好多东西要写，因为这些东西是我们之前讲过的。So okay, today I'm going to be a bit rush because the concept, the idea we already seen before. Actually, you should think of the whole chapter of fundamental group of circle. So we are actually follow the same tempo, same thing here. And if any case I meet anything new, maybe I'll slow down a bit. Otherwise, these are the abstraction of the how you lift map in how you lift map that map into S1. Okay, so the P there actually is the covering space map. Okay, so if you have any kind of covering space here, then you can define a lift as well. Okay? That commute with this P or factors through this P. Okay, actually F factors through F tilde. Okay, through this P. Okay, and the next lemma is a quite technical lemma that we're gonna use that to prove why we can lift homotopy. So this lemma is, if you have any two lift, okay, then the set where they are equal is both open and closed in image. So if Y is connected, happen to be connected, this set should be empty of the whole Y. Okay, so meaning they will agree. If they agree at some point, they should agree at the whole connected component. Like that.
I can only prove after that.
Yeah, because that one is because this one is the general topology segment. So the first one is to prove the open and close. So to prove this is not as hard as you think. It's also a general topology question. So meaning you need to find an open neighborhood around that also satisfy this. So you have a point that satisfies this equality here. You need to find an open neighborhood that contains this point, also satisfy this property. Okay, this is the technicality. Not too far from general topology type of question. Close is also the same. You need to prove a closure. Okay, but the idea here I want you to remember is, as long as you have two leaves that agree at some point, they should agree on the whole connected component. This is also something we prove for the map on S1, right? Yeah. Yes. Yes, exactly. Yes, exactly. Okay, but this one is more general. So you need to use the more general statement, argument to prove it. Okay. So it's worth to have a look. Okay, it's quite standard. Okay, you use you see, you just find an open set, okay, that live in Y and satisfy this equation. And then for close, you also use something about closure. Okay, also general topology type of argument here. Okay, let's skip this. Next, okay, this one is very important. We can lift a map. We also should be able to lift a homotopy. So let's say you have a homotopy from F0 to F1, and then you can lift F tilde. Once you can lift F tilde, then you should be able to leave the homotopy. Okay, so you should think of this F0 tilde as a starting point of your leaf of your homotopy. Okay? This is the starting point. Okay. So where to end? It depends. Okay, it depends on your leaf. But this leaf is unique. Okay, so your F1 tilde is also unique. So where this H tilde blah 1 will end is something that is decided by your H tilde. Okay, so this is also unique. So the one we prove for S1, we also show that it's unique, right? I still remember how we prove for S1. I didn't prove in class, but I show you the picture, right? You need to like make into product of those and then you cut. You remember? I don't remember. I remember the long proof, the 10-page proof. Yeah, that one. Okay, this is the generalization of that. You also need to use the Lebesgue number lemma. Yeah, use the Lebesgue number lemma. So you leave open set by open set. Okay, you leave open set by open set. Okay. So this you should expect also 1, 2, 3, 4, 5. 5 this only 5 pages. Huh? If you want to write it for the S1 case, it's very long. But yeah. Actually, this is what Hatcher present first. Hatcher present this proof when he do the fundamental group of circle. Yeah, he did this one. That's why you can understand. But what he do was he proved a general statement and then he used it for the specific space. Okay, and then corollary is we can leave path, okay, because you can think of homotopy as think of a path as a homotopy of one point. Okay, so you can corollary is you can leave path as well. Okay. Yeah. So okay, all good. So leaf, if your leaf agree at one point, it should agree on the whole connected component. If you have a homotopy and then you can leave one of your map, then the other, then the homotopy can be lifted. There's a unique one. Okay, so a very important result here is they are unique. These leaves are unique. Okay, if it is not unique, what you need to do is there's a choice involved. Maybe you need to pick which leaf you like or you want. Okay, but here there's no choice to make. Okay, there's unique one. Okay, this one also kind of standard or similar to what we learned before. If you have two paths and then two leaves that lead to the starting at the same point, then their leaf should be homotopy. In particular, their endpoint should be the same. Okay, this is the very important thing. Okay, the endpoint has to be the same. Okay, similar to the R case. So this is another corollary. And then the last one is why we justify our number, how we justify our number of sheets here. So we have a coverage space and X is path connected. Okay, then P inverse of X actually are all divided. So they are same number. So the number of sheets is well defined. It can't be like, oh, this point have 5 pre-image, but that point has 6 pre-image. No. Okay, this cannot happen. Okay, they are bijection. Okay, every point has same number of pre-image. So the number of sheets is very well defined. Okay. How about maybe we can start proving the next one. One is interesting. Maybe we can start prove this. So as we observed just now, if you have a coverage space map, then you also have a map induced on the fundamental group. Does it make sense? You have a loops on S tilde, then you map it down, it's still a loop because at the top You look back with your pre-image of the base point, you map it down, it's still that base point. Okay. But the point here is it is injective. Injective means what? You can think of it as a subset. Okay, sit nicely as a subset. Okay, so actually the loop you see at the top and the covering space is already a loop inside your base space. Okay. 一样，你现在是不是在学 fiber bundle 啊 ？base space 很熟，是不是？fiber space 跟 base space. So you can think of the covering space as a fiber. Okay, and then there's a codomain space as a base space. Okay, the image subgroup consists of the homotopy classes of loop in X based on X naught whose lead to X tilde study and X naught loop. Okay, this last sentence is what we discussed just now. Thank you. Okay, maybe we can prove this. Let's prove this. I think this proposition is kind of magic. Actually, not very hard, but we can have a look. Okay. Yep. Obviously, 啊，不要搞事情。Obviously, yeah. Why is it obvious? Is it obvious? Yeah, obvious because when we write P like that, right? We will mean that we map PS tilde to PS to S. 就算不是你也可以 conjugate 嘛 ，doesn't matter by array. We can conjugate. Yeah, conjugate. If you conjugate, they are still the same. Isomorphic group. Doesn't matter. Okay. Okay, so how to prove this? Injectivity, ma. You just assume let gamma, okay, let gamma I to S tilde be a loop based at S naught tilde such that this is mapped to the identity map, and then you want to show injective, you need to show that this gamma homotopy class of gamma here is the identity map inside your pi 1 of S tilde. Okay, so how to show that? So you need to produce a homotopy, okay, inside your S tilde. Okay, you need to produce a homotopy inside S tilde such that this gamma here will homotopy to identity. Okay, but from this equation here, what did you know? Actually, you know that the projection of this gamma is homotopic to identity. Enough or not? Enough. I got homotopy in the base space already. Okay, so just now we say that we can lift this homotopy, right? So let's say this homotopy is via H. So then we can lift H. Okay, lift H. Lift H to what? Lift H to H tilde from gamma to a lift of ES naught. But what's the lift of ES naught? And what's the lift of ES naught? What's the lift of ES naught? Constant point. Leaf of S naught, isn't it just P inverse of X naught? Okay, but maybe your P inverse of S naught got a lot of points, right? But I guess we fix all our leaf that start at. We fix all our leaves starting at X naught tilde. 问题 Sorry. Gamma is a loop in so this gamma is a lift of P composed with gamma. So gamma is a loops in the covering space already. That makes sense. Gamma is already a loops in the covering space. It is already a lift. Okay, it's a lift of what up? It's a lift of the projected gamma. 打下去啊，因为 because we want to show homotopy in the covering space. That's so the point here is I need to produce the homotopy in the covering space to identity. Okay, but the identity loop should be the homotopy should link to the leaf of the identity loop in the base space. Okay, so that loop start at X not tilde, and could it be anything else other than identity loop? I don't think so. There's only one link for the identity loop, right? It should be the identity, which is identity loop at X not tilde. Does it make sense? Because just now we proved that a path lifting is unique, right? So this is one of the leaf. The other leaf should be homotopy to this one. So this the identity loop. Okay. Yeah. Because path lifting is unique. And then this is one of the lifting you can have. Okay, every other lifting should be homotopy to this. Get it? 为什么 project 我要 lift 回上去 very good, because how we get the homotopy in the covering space is by the homotopy inside the base space. Makes sense? We lift the homotopy in the base space up. Otherwise, we don't know how to construct this homotopy to identity loops. Okay. Next part. What is the next part? Oh. So the next part is just to show that the image, to describe the image of the pi 1 of X tilde. So image of pi 1 of X tilde is a homotopy class of loops in X base and S naught whose lead to S tilde starting at S naught are loops. So you need to show left-right equality, right? Subset, left-right subset. Okay. So which direction is easier to say? So which direction is easier? So if you start with a loops inside S tilde, you project it down, it should be a loop inside X. Yeah. Do I have anything to say? Yeah, 蛮 trivial 其实我在想在哪里不 trivial 要解释一下。 对。No, cannot 分开 cannot 分开 It's like maybe you can 经过 a few different pre-image. 因为 because you are mapping from pi 1 s tilde. If you are not okay, because you could imagine that a path in an x naught could lead to a path could lead to a loop that's not starting at s naught tilde. It's possible, right? You get what I mean? For example, let's say this map, let's say this map. Hey, oh sorry, not this far. It's the other far. Because it could happen that if you look at this case, because a leaf is just a choice, So there are few choices. So for example, if you look at this covering space, if I want to leave A, I can leave to the left A. Left A is a loop. But if I leave to the right A is no. So leaf is a choice actually. Okay, you need to.
So actually, this proposition is just to say that it's just if we consider the picture, that picture A is in the image, but B is not in the image.
Yes. Yeah. Although you start with S not tilde, but you are not a loop. So you need to satisfy two conditions. One, you have to be a loop inside your S tilde. Second, you need to start with S not tilde. Yeah, S not tilde. So in this case here, so to translate the language from what we have just now, so S naught is the bottom one. Wait, this one too big. This one is S naught. Okay, then this one is S naught tilde. Okay, maybe the other one I called it S naught tilde prime. Okay, so if you leave your A to S naught tilde prime, you are not looped there. And then you are not starting at S naught tilde. Answer what?
For example, the image of that map P star is just a P star.
Z map P star.
I mean, the image of P star is just a P star.
Image under P. Yeah. Exactly. Yeah. So this is what we call the P star of pi 1 of, let's call this x1. So x1 of x naught tilde, or just call it s tilde, is equal to this. Okay, latex 跑不出来。Yeah. True. No, I mean like the leaf I talking about is the F tilde leaf. It's not the P inverse leaf. So your F tilde should like stay inside P inverse. P inverse is inverse image, right? Leaf is pick a specific leaf. So you could pick your leaf to S naught tilde, or you could pick your leaf to S naught tilde prime. This leaf could be different. You understand? So the leaf that I'm talking about is like the different kind of pre-image you can take. So for example, so let's say this is A, okay? So this A could be your, so this is A, okay. Right, so let's call this A1 and A2, okay? So your A tilde could be A1, or your A tilde could be A2. Or is it better that I put A tilde as A tilde prime as another A like that? Is it better? Yeah. Okay, so this A, you should think of the leaf of A as well. You can leave A as well. You not only can leave homotopy, you also can leave path. So your path you can leave to either A. Sorry? But in S tilde, we need to pick a base point. Yes.
And that one
Sure, why not? Because you what do you need to satisfy? After you lift, you project down is the same thing. After you lift, you project down is the same thing. So based on your projection, you lift it up, you project down should be the same A. And that's it. Nothing about base point, nothing about.
Otherwise, the B cannot give.
What do you mean?
You mean I mean that in the original, the B is a loop. So when you lift it up in that future, the B should start at the end and then jump to the two parts.
As long as the two pre-image of S0 is fine.
Yeah.
So at the bottom is a loop. You can lead to non-loop.
Yeah.
Yeah, you can lead to either
Because the pre-image can make
yes. As long as after projection you go back to the same loop. That's fine. Okay. Does it make sense? Like what you need to satisfy is P on A tilde is equal to A. That's it. This is the covering. This is the leaf property. Okay, your leaf have to satisfy this. If you satisfy this, then done. There's no base lifting. I think later we got base lifting, but now don't have. Okay, huh? Hmm. Huh? 第四个啊，T lifting T I mean lift or you mean lifting? You mean covering space? Covering space? As long as every point that exists open neighborhood such that you can write it as such that the pre-inverse of that open neighborhood is a disjoint union of open set that map homeomorphically into the open neighborhood. Okay, and then the definition of lift is as long as you commute with this projective, not commute, as long as you form a commutative triangle with this projective, no, not projective, the covering space map. Okay, yeah, these two pieces of definition you need to bear in mind a lot. Okay. I think a non-trivial one is going from P star pi 1 S not P1 pi 1 S tilde to the homotopy class of loop that start at S not tilde. I think this one is more non-trivial, right? Oh, sorry, I think wait, let me see. Which one is more non-trivial? After you map down, yeah, after you map down, then yeah, okay. I think this is more non-trivial. So if you have loops inside here, okay, if you have a loop inside P star of pi 1 S tilde, why is it true that you have a leaf that start at S not tilde? Why? If you have a loop that in P star, the image of P star, why this loop has a lift that start at S not tilde? Because you can just pick any pre-image of S not to start with. Right? Because you can just pick any S not tilde to start with. But why are they isomorphic? Why are they homotopic? Why are they homotopic? Yeah. So a loop that represents an element of an image of pi star is homotopic to a loop having such a leaf. Why is it homotopic? So if you have a loop in pi 1 and then you map it down.
Now,它的里面不一样的 base point，我就在它是会存在一样的，我用一样原流没有去上接它。
But then how do you know that that loop have the same leaf? So if you have an element in the P star of pi 1 x, and then obviously you are loop with pi 1 x naught. Then is it obvious that the leaf of this guy? Yeah, I think it's just chose. It's just picking the leaf of that loops. But yeah, I think it's just picking the pre-image, picking the one of the pre-image to start. Okay, so I mean, yeah, but yeah, I think it's just picking where to start, and you are free to do so because it's homeomorphic. So you can start with any pre-image you like. Okay. Yeah. So axiom of choice. Axiom of choice. Yeah, sure. Yeah. Sure. Sure. But when we fix one S tilde, S no tilde, then meaning we know that exists already, I guess. Somehow know it exists. Yeah. Yes. 一开始 actually 我们知道我们要什么，不是我们不知道我们去找好吧？我们知道。Yeah. We fix one. Okay. Actually, we have control on the covering space. We know what it looks like. Yeah, that's the question. Let's do a few more minutes before we go into quiz. Okay. Next proposition is the number of sheets of covering space such that S tilde is path connected is equal to the index of the image of pi 1 S tilde in pi 1 x. Okay, this one very interesting. So the number of sheets can be computed using index. Index, do we need normal subgroup to define? Yes, right. Okay, but we know that pi 1 actually is a normal it's normal because under conjugation. Okay, it's the same group. Okay, I think this one I also left it for you. This one is a bit like AA proof. Plus a little bit of half. And then second one is given covering space and the map. When can we find the lifting? Okay, when can we find the lifting? if and only if the f star of pi 1 of y is in the p star of pi 1 of x tilde. Okay, so does this repeated what we have known? Let me see what's the difference. Previously we said that we can leave half, okay, and then we leave homotopy. We haven't really leave any map yet. We haven't really leave any map. We just define a leaf. So we want to see when does this leaf can exist. Okay, it exists based on the criterion on the fundamental group. Okay, so maybe I should draw this triangle out. It's easier to appreciate this lifting criterion here. So you have a triangle like this. So you have y naught, and then x tilde x right here, and then x naught here. Okay, so you have a f going from y to x. This is a base map, so you want to send y naught to x naught. And then when do you have a f tilde here that can commute to p if your pi 1 of y x naught, okay, under this induced by this f is actually living inside the pi star of pi 1. Okay, you need to make sure the inclusion of this. Okay, so meaning the pi 1 of y naught here under this f should be part of the image subgroup of P star here. Okay, does it make sense? Does it make sense? Meaning the loops that cover by the image of F should be a loop. Should be a loop in S tilde. Only then you can lift it up. Otherwise, you cannot lift. You can understand? Because if there are more loops here, there's no loops to recover the S tilde loops, so you cannot lift it. So a loops inside this y tilde here must be a loop inside S tilde. Only then you can lift this F. Makes sense, Okay, because if you have more loops inside your pi 1y or the image of your pi 1y, then your S tilde cannot help you to produce the element. Because it may not be a loop. Yeah, because it may not be a loop at the top and then at the bottom is not a loop. Then you have some problem. Okay. And then we have a uniqueness here actually as well. How about we prove this next time? We'll prove this next time. Okay, we'll prove this next time. And then there's a uniqueness property here. Okay, and then this leaf is actually unique as well. Okay. So far, any question? No. Okay, so today what you have learned, you can leave path, you can leave homotopy, you can leave map, as long as the fundamental group subset inclusion satisfied. And then you have uniqueness criteria on this lifting as well. As long as they agree at some point, they should agree at the whole. Does it make sense? Okay. So throughout these few weeks, you keep observing phenomenon is you have a lift. If they agree at some point, they should agree at the whole connected component. Okay. So let's start the quiz. So I'll just give you 10 minutes to unpack. Okay. Okay, 不用考题目啊 you put your name and put the quiz is fine. 赵生要做咩？ No need to copy 不用 copy But right now the question number just draw.
Yeah, just draw. Drawing class.
Hey, you can buy.
Okay, just draw this. 不用爬，不用爬，浪费时间。Okay, but write down the question number 1A, 1B, 1C, 1D. Still got one. Let's put this 1E lah. But this E is not the question. Okay, maybe 2 lah. Argue all 4 in question 1. Okay, this is number 2. Number 2, number 1. Okay, argue loosely why all 4 in Q1. All 4 spaces. Okay. Homotopy equivalent. Okay. No need to give me full proof. Just tell me what space can be contractible. And no need to give me the full proof. Write down what the S/A. Just tell me what subspace is contractible to get to the other. Okay. Put down your name, student ID, and then the quiz number, question number. No need to copy. Please draw. As nice as possible. If you cannot recognize, cannot give mark. Let's see your drawing skill.
像我们这样画画，
进来啊，进来，进来，他们考试，进来。Yeah. If you don't understand the question, you can ask. 我也不用聊天，可以问我问题，但是不可以聊天。对，不要画破洞了。
问他，你不在想什么？那你
Torus with at least blue in x1 cross 1. So you should think of x1, one of the x1 as the 0 to 1.
but the one can be
Sure. Depends on how you start, right? Well, I should say that this circle should be the same as this circle as well, right? x1 cross 0. These two should be the same, certainly, because you are Taurus.
Yeah, so the contractible subspace, maybe you can highlight the space you want to contract. Then should be. Yeah, if you don't have color, you also can just like make squiggle around the subspace. And then tell me that you want to contract that. Hmm? You can make a note on your diagram because you need to tell me the subspace, right? You can make a note on your diagram because the subspace obviously live on the diagram. Hmm? No, T2 是 T2 is all the vector that we're studying. Everyone almost done or not? 2 more minutes. Oh, I see some nice picture. Okay, everyone done? You want to discuss or not? Or just hand it to me? You want to discuss? Huh? Yeah, yes. So as long as you found one direction. Okay, eh, uh, done. Maybe 小月好了吗？可以了，可以了吗？OK，帮忙收一下。You guys want to discuss or you want to go back? Can you see answer? What's the answer? Okay, just roughly see. No need to mark. I just discuss. I'll mark myself. Maybe I show you your beautiful drawing next time. Okay. Let's quickly talk about this shape. Okay, so what is A? A sphere. So you start with a sphere. Okay, with a line joining the south and north pole. How do you draw? Maybe you can go outside. Actually, you can go inside as well. Doesn't matter. Okay, thank you. Okay, you can go inside as well. Okay, how about wedge sum? Wedge sum of S2 wedge S1. So how would you draw? How would you draw? Okay, you join X1 at a point, right? Okay. Actually, you can attach it inside as well. Okay, you can attach inside. Okay, how about next one? What's the next one? The sphere with north and south pole glued together. This is the one we discussed in class, right? The cross-zone, right? Okay, so maybe you get the cross-zone. Have to stick together. And then there's a hole here. Actually, there's another one. The red bean bun. So you can draw like this. Okay, the red bean bun. Wait. Okay, the red bean bun here. And last one is the new one that I haven't shown you in class, right? So basically, you just take your torus and then fill your torus here. Okay, there's another way. There's another way. There's another way. So there's another way is putting here. Is what the picture want you to do. Okay, these are equivalent actually. Okay, so how to collapse from 1 to 1. Let's say we can go from A to B. Okay, from A to B where we can collapse. We can actually collapse this one, the one I show you in class, right? Collapse this A to B. And then A also can go C. A, how to go C? You just collapse this line here. A to go C. So we got A to B, A to C, right? So which one we haven't reached yet? How about D? We can go D from where? Let's go to D by C. Is it possible? Go to D. Sorry, did I say something wrong? Go to D by C, sorry. Go to D by C. So how do we go? So we just collect this. Okay. Yeah. But homotopy equivalent is equivalence, right? Relation. So you just go one way, then it's fine. Okay, any question so far? No? Okay, if no, then I will see you on the next week. Okay. I don't think you have 你可以用 collapse 嘛，你要用另外一种方式啊。